Dear students, I welcome you for the lecture related to the block diagram reduction in the process control. Now, this is a simple system which is showing the three elements in a series where G1 is the first element having the transfer function G1, G2 is the second process unit having the transfer function G2, third block is the third process unit having the transfer function G3. I don't know they are either first order, second order, or the uh, non-interacting system. So input to this is the U and the output from the system is the X3. Now from G1 also there can be certain output, that is X1. From G2 also there can be certain output X2. So from G3 the output is X3. Now when I will write the transfer function as the G1, there I can write the output Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. So for a G1, that is the Laplace transfer function of a first system, that is I can write x1 upon u, that is what? A Laplace transform of the first deviation variable. So I can write u into G1 which is equal to x1. That is what I have write. G1 into u which is equal to x1. Similarly for G2 also I can write G2 into x1 which is equal to the x2. For G3 I can write x3, that is the output upon the input. So x3 I can write as G3 into the x2. So this is a simple three blocks are provided in a series. Now what will be the resultant of these three blocks? I cannot develop the system in terms of these three blocks. I have to reduce that by considering all the different factors. The G1 that can be for a controller, G2 that can be for a control valve, G3 that can be for the process. Now in this we have not provided the feedback system because we are simply considering the primary stage first. So this is then by successive substitution for this I can write x3 which is equal to G1, G2, G3 into the U. So x3, that is G into U. So I have combined all the G1, G2, G3 as a one transfer function G. So where G is equal to G1, G2, G3. So I have reduced these three blocks into a single block having the transfer function. Instead of writing the three transfer functions, I am writing only one transfer function. That is what? I have reduced these three blocks to a single block system. But my output is x3, same as here, and the input is the u, same as here. So keeping the inputs and the outputs constant, I have manipulated or reduced the three systems, and the transfer function has been manipulated into a single one. Now coming to a bigger size. So this incorporates a lot of transfer functions. But in general, our basic system that remains the same. Certain block diagrams, a comparator is there, set point that is provided, a comparator is there, a feedback that is there. But in this case, there are two comparators that is present. In this case, there can be the two comparators that can be present. Then There can be two load variables also. D1 and D2 are the two load variables. One is before G2 and another is after G2. That can also happen. The systems that can be become more and more complicated as you go further. So now how to manipulate with this? That is, we are going to first consider only the inner system, inner loops. That is, we are only considering this inner loop first. And we will reduce this inner loop transfer function into a single unit. So there are G2C, G1C and GM2 and E2 is there. So that is represented as the G4, which is incorporating G C2 G1 upon 1 plus G2 G1 GM2. So I have reduced this system as the G4. So all this system incorporating has been reduced to the G4, and I am writing GC1, G4, G2 and G3, right? GC1, G4, G2, G3, and similarly your two load variables are there. Then in the next step, I am going to reuse this complete block diagram where the output is Y and the input is YSP. So YSP and the Y, which is incorporated the G5. So G5 is reduced to this thing. So this is what step by step reduction that is going to happen. How that reduction takes place, that also we will see. How G4 that reduces, how G5 that reduces, that also we will see. Now there are different set point change is there. There are servo mechanism problem and the regulator mechanism problems are there. There are two types of the problems which exist. One is the servo and second is a regulator problem. Now what is servo? That means a change in the set point. The closed loop transfer function for a set point change. The closed loop system behavior for a set point changes is also referred to as the servo mechanism problem in the control system. So the control variables with a change in a set point, that is known as your servo mechanism problem. Now in this servo mechanism problem, what happens to a load variable U? Only in case of a servo mechanism, it is dealing with the set point. It is not talking about the U or the D1 load variables. Load variables के बारे में कुछ नहीं है. Load variable change in the load variable is 0. That is what du upon dt, which is equal to 0, or in this case d1 upon dt equals to 0 and d2 upon dt equals to 0. That means the change in the load variable is 0. Load variable does not vary with the time. Only the set point that can vary with the time. So these are called your servo mechanism problem. Now second category is your regulator control problem. So regulator control variable is changing with respect to the load variable. Set point is fixed in this case. Now consider the case of disturbance change. Disturbance is your load variable. So which is also referred to as a regulator problem. So that is your regulator problem. So in case of regulator problem, it is the dr upon dt, which is equal to the 0. That is regulator problem dr upon dt, which is equal to 0, and it is taught in terms of C upon U. That is, output is the C and input is your U. This happens for a regulator problem. For a regulator problem, change in set point is 0 and it is talked in terms of the U, change in the disturbance change or disturbance variable. And for this servo mechanism problem, there du upon dt, that is equal to the 0, equals to the 0, and what is to be calculated? C upon R, that is to be calculated for this servo mechanism problem. It is talked in terms of the output and this set point, and this regulator problem, it is talked in terms of the output and in load variable or disturbance variable. Understand the difference between this servo mechanism problem and the regulator problem. C upon R, that is related to the servo mechanism problem, and C upon U, or the output upon the load variable and the output upon the set point. That is what the servo mechanism and the regulator problems are. So servo problems for a negative feedback system. Now this is a simple control system, servo problem with a negative feedback system we are going to talk now. How the block diagram that is reduced. So what is there for servo problem? It is talked in terms of C and R. So there is change in the load variable, that is 0. The same block diagram that is there, no change in the block diagram or previous same block diagram that is existing. The same block diagram that is there. So this is the same block diagram that is available, and we are only manipulating with that. So GCGV, that is combined to give you the M and E output variable by simply P, which is equal to the GC into the E, M which is equal to GC into the P. Then this is the first reduction of this block diagram. Then second, this can be written as GC, which is equal to the P upon E. This is what GC, which is equal to P upon E. Then GV, which is equal to M upon P. And so GC into the GV, which is equal to M and E. Then at this, the load variable, that is 0. U is remaining constant, so change in the du upon dt, that is 0. Then block diagram that reduces to the Gp, which is equal to C upon M, Gp, which is equal to C upon M, and therefore Gc, Gv, Gp, which is equal to C upon E. Combining these two blocks, this is reduced to this thing. Then this figure has been drawn here also. So reducing this H, which is equal to the B upon C. H input is C and the output is the B. And the error that will be generated, which is equal to the R minus B, which is the error that is generated. And R minus B, which is equal to the HC from this equation, E which is equal to R minus HC, E which is equal to the R minus HC. So this GC, GV and GP, which is equal to the previous case, it was C upon E. So substituting the value of E from this calculated value, you will get C upon R minus HC. And then after further simplification, GS overall, which is nothing but C upon R, which is equal to GC, GV, GP upon 1 plus GC, GV, GP and H. So, what can be generalized in this case? That is, the GS, the overall transfer function, which is equal to C upon R, that is C upon R, which is related to the servo mechanism problem with the negative feedback system. So, this is the product of all transfer functions between C and R. Between C and R, the product of all transfer functions, that is GC, GV and GP. This is GC, GV and GP, that is the product of all transfer functions in a numerator, and in the denominator 1 plus product of all transfer functions in the entire control loop. That is the difference in the entire control loop. That is entire control loop, that is incorporating the H also. So that is 1 plus GC, GV, GP into the H. This is what is the generalized statement for the servo mechanism problem with the negative feedback system. That is the product of all transfer functions between the C and R upon 1 plus product of all transfer functions in the entire control loop. This is the servo mechanism problem with a negative feedback system. So similarly, we can have this servo mechanism problem. This is what the above case C upon R, which is equal to GC, GV upon GP upon 1 plus GC, GV, GH. And in a block diagram, this can be represented as C upon R into the transfer function, which I can write GS for the overall system, which is equal to C upon R, which is equal to product of all transfer functions between C and R upon 1 plus product of all transfer functions in the entire control loop. So, this is for the negative servo problems with a negative feedback control system. Now, the servo problem with a regulator problem with a negative feedback system, C upon U, is your regulator problem. C upon U is your regulator problem, but with a negative feedback system. So, after generalization, the same equation, only difference is that you will get or you are calculating the C upon U that we are going to calculate. C and U. So there you will get the product of all transfer functions between C and U upon 1 plus product of all transfer functions in the entire control loop. So that is what the basic difference C upon R and C upon U. जिसके इन दोनों के बीच में के प्रोडक्ट ऑफ ऑल ट्रांसफर फंक्शन दोनों जगह पे वही है. So GP is only the transfer function in between C and U. So this is what C and U के बीच में सिर्फ GP है upon 1 plus GP GC GV into the H, the product of all transfer functions in the control loop. So this is for the regulator control problem with a negative feedback system. Now similarly I can have the servo mechanism problem with a positive feedback system. What is the difference? In case of a positive feedback system, it is only the change of the sign that will be observed here. Instead of this is 1 plus GC GP into the H, it will become 1 minus GC GP into the H. माइनस साइन है तो आपका पॉजिटिव फीडबैक है. दिस इज फॉर द पॉजिटिव फीडबैक. सर्वो मैकेनिज्म विथ पॉजिटिव फीडबैक will have the negative sign here. Similarly, the regulator with a with a positive feedback system will have the negative sign here. That is only the difference. So similarly, you can work out for the different regulator problems